Yeah, let me thank Kai for inviting me here this week. So my talk today is going to be about machine learning for quantum many-body physics, essentially. And so specifically, the type of machine learning called generative modeling, which allows you essentially to learn probability distribution from data. And so I'm going to tell you how to repurpose that to essentially learn wave function from data that can be generated in experiment, but also from simulation, classical simulation. Okay, so let me first say like a couple of words about the Torlai Institute, and I know how many of you know this, but it's a recent institute from the Simons Foundation in New York, and as you can see, that is the focus of the institute is really towards computational sciences. So we have several centers. Another one in neuroscience is coming up, and I'm at the Center for Computational Quantum Physics. And the focus of our center is really in quantum many-body physics, so physics of many interacting particles. And I would say there is an equal effort towards physics, so like electronic structure in real materials and molecules, synthetic quantum matter engineering in the lab, like cold atoms, and quantum hardware as well, but also towards methods, so software development and algorithm development, and so on. And so the problem we focus on, we can call it the quantum many-body problem, is really the intrinsic complexity that arises in systems which comprise a large number of interactive degrees of freedom. So again, there could be electrons in real materials, but quantum bits of information in quantum computers too. Okay, and so for the typically when we look at these systems, what we're trying to do essentially is solve the Schrodinger equation. So if you're interested in some out of equilibrium dynamics, that you would look at the time-dependent Schrodinger equation, or if you're interested in the ground state of a condensed matter system, then you would solve the time-dependent Schrodinger equation, or maybe you also want to get some elementary excitation out of this ground state. And so what typically we look at kind of simplified models on a lattice, for example. So the Hadbar model for interacting electrons, that's kind of what is believed to be underlying high temperature superconductivity in like transition metal oxide and these materials, and it's kind of the holy grail of condensed matter physics, and still puzzles the community. One could consider like spin model, so frustrated magnetism, which underlies spin liquid states, or molecular structure, where you have the quantized fermionic Hamiltonians on some orbital structure. Right? And so, what we do essentially, we develop classical algorithms to solve this problem. And as you all know, if you want to solve like the ground state of some Hamiltonian, that's a fairly simple problem. It's not really deep. You just have to build this Hamiltonian and like diagonalize it. But as you know, this problem entails like some really exponential complexity, since the Hilbert space for your system, say if you have spins, really grows exponentially, like with the number of particles. So if you try to really brute force these problems, so for example, doing some exact diagonalization, the time that you need, that you need to reach simulation solution or like memory too, say really exponentially with the number of particles. Okay. So that's a no-go. And even if you get clever and you encode symmetries, you still can get to some 20, 25. I guess the largest simulation they get to 50 electrons or something like that, but you really cannot get much higher than that. Some emergent phenomena really you can become crisp when you look at the thermodynamic limit, or a very large number of particles. And of course, there are other techniques that we develop, like these are two that I'm more accustomed to, but there are others, tensor networks, where we really try to find a compression of the wave function in terms of a network of tensors, and quantum Monte Carlo, where instead of really looking at the quantum problem of particles, we really try to map this into a classical problem, really here maybe in the path integral, you have like Vauban strings in D+1, and you sample this object to extract observables like correlation function and point function, etc. And each of those come with their own strength and their own cons, right? Of course, there is a different way, as suggested by Feynman already in early 50s, when he was thinking about miniaturization, is really to exploit the rule of quantum mechanics to do computation. And then this was become defined in the 80s when he proposed really the idea of quantum simulator. Okay? And so in terms of quantum simulation, I guess there are two ways that one can go about it. Is really, if you want to solve some underlying properties of the quantum matter, you can map these into, like a quantum algorithms where really you solve the problem by devising a circuit model where you apply a series of quantum gates. So in this case, for example, if you want to solve the dynamics of given some Hamiltonian, then provided some quantum state preparation, you can essentially express this unitary evolution through a series of gates. That's how a quantum computer works, right? It's like unitary dynamics. And this is kind of similar to, what is done in like superconducting architecture, like the Google one or IBM. Or, I guess this is more in the spirit of Feynman's idea, is really to try to find some other physical system which we have more control over and like emulate the physics. So for example, if you want to simulate electrons in these copper oxide materials or like Hubbard models, like one can do is that you can essentially build an artificial crystal, for example, like an optical lattice with lasers, and then load fermionic atoms into it. And the advantage is that you can really engineer interaction. So you can really drive this system in regimes that may not naturally occur in real materials. So that's very interesting. And so as a result, essentially, with recent advances in this kind of technology, from like trapped ions to neutral atoms and superconducting qubits, these laboratories essentially produce like a large amount of like high quality data, where we can really go and probe this system at the single atom level. So you can get like single picture where each single component can be addressed individually, okay? And really what underlies this picture is the quantum state that this hardware produces. Okay, so the motivation was really to try to take all this data that is produced in laboratories and extract as much information as possible. In fact, each of these experiments comes with its own constraints. So you can produce this data, but there are some measurements that are very trivial to do, some other measurements that are complicated, maybe they entail really like a large overhead in the resources that you need. So the thinking about machine learning was really an efficient way to process all this data. And so we can take this technology and apply it to this type of data. But of course, like I'm a computational physicist, so I can also go and code, do computer simulation, and generate synthetic data. So for example, this is a quantum Monte Carlo simulation of a resonating valence liquid. And this is equally important because it really allows us to look at the ideal case where we look at the exact wave function and we can really understand range of applicability of our machine learning algorithms, and as well as verify often application to actual experimental data. And so I'm going to look at a specific problem here, which is really the question of can we access and can we learn the quantum state from a set of measurements. So this is traditionally a quantum tomography problem. And the setting is very simple. We have a physical system, and this, whether this is hardware or cold atoms, and we can prepare, let's say with high fidelity, a given quantum state, and then we can make measurements on it. Those are typically projective measurements. The projective measurements essentially can generate data, and this data is distributed according to some probability distribution. And the Born rule tells us, how this probability distribution and this data is, related to the underlying quantum state, right? So the idea is, essentially to, engineer this back and get the state from the data. And there are two ingredients that you need to do that. First, you need the representation of the quantum state. That's what we want to get out of this whole process. And the other is a way in algorithm essentially that extract this information. So full tomography really represent the quantum state in full. You write down all the elements in your density matrix or on your wave function, and then you can do maximum likelihood learning or other sort of data processing. And another very successful technique is MPS tomography here. Essentially, you're approximating the quantum state by a matrix product state. So you're putting like an assumption on the structure of the state that you're reconstructing. So And here solved the problem that really full tomography was restricted to very small system, clearly the system that you can represent in full, so again, handful of particles. Okay, is everything clear? Any questions? Like, please do interrupt me if you have any questions. And so, the idea of using machine learning here, it felt kind of natural because, in particular, neural networks, because what neural networks do at the end, they are a way to find some, well, let's call it efficient for now, some representation where you take this high-dimensional data and you compress it into some low-dimensional feature, which are the weights in your network. So they're very, it's very natural to think about this type of tools as a way to represent quantum states. They call it the curse of dimensionality in data science, which is really reminiscent of what we face in quantum mechanics. And the learning algorithm, that's also natural too, right? Machine learning, they take data in and they discover features and patterns, very generally speaking. So it really sounds like we could really do tomography with repurposing this algorithm. And I'm going to show you that under certain circumstances, under certain assumptions, really standard, industry standard machine learning corresponds exactly to state tomography. Okay, so there are different types of machine learning. This is not what I'm really going to talk about. I just have these slides to just tell what supervised learning here is. And in supervised learning, I guess all of you heard about image classification and pattern recognition. Here is really the goal of supervised learning is really discovering some conditional dependence between some input, say images, and some label, some categorical feature, right? So you can imagine having some input to this neural network as picture of zeros or one, or cats and dogs, whatever you prefer. Of course, you pixelize this in some way. And what the neural network does here, it just approximates a function which takes an input, the image, and outputs like a label, okay? So really the function that you're trying to learn, approximate, is a conditional distribution of a given label, given some input, okay? Which is unknown, but you do have data. And essentially, the idea is to use data to discover this. So the neural network really is a parametrized model of this unknown distribution, and you train this network so that, if you are successful, you feed an image into the input layer, you propagate the signal through. These are just linear algebra matrix vector multiplications, and you're going to get some output at the end with higher probability than the other. And you want this output to be the correct one. Okay, so I guess this is the most common type of machine learning with neural networks, but this is not what I'm going to talk about. And this has been applied to several areas in many body physics and condensed matter. You can imagine, these images, instead of being zeros and one, to be pictures of STM images or cold atom picture, and say, well, I want to distinguish between having like a superfluid state from like a Mott insulating, and try to detect quantum phase transition in this way using the same. And this has been done in actually experimental with experimental data recently, or even to like Fermi-Hubbard quantum simulators in like Marcus Kreiner group. So the other type of machine learning is called unsupervised learning, and it doesn't really require any label. It's just raw data. So you can imagine to having just some raw data here. Those are like, could be binary bit strings, same as before, but there is no associated label. So the goal here is really to have some kind of way to detect features so automatically. So you can imagine clustering. Clustering is a type of unsupervised learning algorithm. You want to find some more dimensionality reduction. You want to find some feature within the data which allows you to distinguish between different clusters. The type of unsupervised learning I'm going to talk about mostly is generative modeling. Generative modeling here, it's really essentially use the data to access the full probability distribution. Okay, so you can have images of cats, all the cats you want, and you want to train a model so that you learn the underlying distribution, whatever that is. Okay. So here you have this black box which contains this probability distribution over the phase space is still this exponentially large space, and this black box produces bit strings, and bit strings are distributed according to P of x. And the idea is to feed these to a network, which again is some kind of parametrization of this probability distribution, and to train these parameters so that your network distribution mimics the data and so the underlying unknown distribution. And the point here is now, you don't just want to reproduce the data, otherwise what's the point, right? You want to be able to generalize past that. So you want to be able to learn enough of the structure that is in the data, but then be able to generalize past that. And if you go to this person does not exist.com, so this is generative adversarial networks called GAN, trained on images, and after you train, you can sample, which means you can generate new faces in this case. And so if you refresh the page, it's gonna just keep printing faces of people that do not exist, essentially. So that's why it's called like generative modeling. Allow you to generate and sample new, sample new states that may or may not have been in the data set, training data set. Okay? So, there are different ways to do that, but the first thing is how you choose this parameterized model. And I guess one of the first model was the Boltzmann machine, was invented in the early 80s, and it was really built on work of people like William Little and John Hopfield. Those were like condensed matter physicists in the 80s that put the first theory of this type of neural network. So that was really interesting. And so in this type of network, you associate a neuron with each of your variables in your bit string. So, we are thinking about working with qubits. If you have n qubits, you associate one neuron, classical neuron, with each of the qubits. And then this particular realization is called Boltzmann machine. You put edges, so you build like a fully connected graph among all your variables, okay? And to each of these edges, you associate a specific weight, a wij. And so what you can do is you can define an energy. This is just like an Ising energy. It is an Ising model, like a fully connected Ising model. These are binary variables with some weight. It could be negative or positive. And you can associate a Boltzmann distribution just by taking e to the minus beta e h e and so on. And so this is a fictitious temperature. You can fix it. And again, the goal is to make this condition fulfill this condition, which in this case was just, can I find an Ising model with a particular set of interactions which actually generates and mimics the distribution underlying the data that I have, okay? And so as usual in machine learning, you have to define a cost function that you have to minimize. So in this case, we want two distributions to be as close as possible. So the good choice is like a Kullback-Leibler divergence, which is like a statistical divergence. It's not, it's in the sense not symmetric, but it essentially tells you how close two distributions are. And so it's just this weighted sum, and when you write it down, you have some like entropy term of this unknown distribution, which does not really depend on the model, and then you have like a log likelihood. This is the log likelihood of your model distribution over the unknown distribution, okay? Okay, well, you don't know the distribution, of course, but you have a data set. You have a data set of configurations. So what you do is that you approximate this measure over the data set. So your cost function really is the average negative log likelihood over the data, okay? And once you have a cost function, then you can just take the gradient and do gradient descent, or one of the many variations of gradient descent that you fancy. And so, the problem really is pushed into an optimization. The specific type of interaction and graph connectivity architecture you choose is going to define an optimization landscape. And then, by just doing updates with data, you're just going to move to this landscape and hope to get to the global minimum. I guess this is a best case scenario. Usually it's much more complicated than this. And once you train, then you can essentially sample this distribution with, for example, with Monte Carlo. So you can draw new configuration out of this learned distribution. All right? So this is not very useful, unfortunately. Actually, it doesn't work. And the problem is that with this particular graph connectivity, you can only capture pairwise correlation in your data. So if you want to learn like parity, for example, that would not work. But there is a simple modification to this, and it's called a restricted Boltzmann machine. And so the idea here is that you have two sets of neurons, visible and hidden, and essentially, well, this is still your qubits, but you lift the space of the network by adding extra neurons, and you restrict the connection. So now it's still an Ising model, but the interaction, it's an Ising model on a bipartite graph. Okay, everything still applies. There is still like an Ising energy. Here you have like magnetic fields, if you will. You still have like a Boltzmann distribution over all this augmented space, and you can obtain the distribution over your visible, the probability distribution of your qubits, just by essentially marginalizing and integrating out this joint distribution, which you can do analytically for the special structure. And you get something out, and there are several properties that for sampling that I don't want to discuss, but one like a punchline here is that it's proved that this type of network are universal approximator of distribution. So you can represent any discrete distribution with arbitrary accuracy, provided that you have enough of these neurons. Of course, this comes the catch, right? You might need exponentially many of these hidden neurons to capture a complicated distribution. So it's really, this already tells us kind of a measure of complexity. How many hidden neurons do I need to capture a given distribution? Okay. And again, everything carries over from the previous case, where we have like this cost function, which is a log likelihood over the data. Here we're just going to have the same cost function over this visible layer, which we can compute. Well, there is a partition function, but we can take the gradients of this cost function exactly and just train this model. Okay. And so from here to do tomography, it's very simple. As soon as you make this assumption, as long as you make this assumption, which I'm going to make now and relax, hopefully if I have time later. And what I'm going to assume is that, I fix like a basis of the Hilbert space, say the computational basis or my sigma z basis for spin model, and I'm going to assume that the wave function that I'm trying to reconstruct, first, it's a wave function, it's a pure state, and the second is that the wave function in this basis can be gauged to be real and positive. Okay, so some of you might not like this, but the point is that, this is true indeed for many Hamiltonian, many ground state of many Hamiltonians, as long as this Hamiltonian is called stochastic. How many of you have heard this word before, stochastic? Okay, more than one, let's go. So essentially the Hamiltonian, the off-diagonal elements of the Hamiltonian are negative, then the Perron-Frobenius theorem tells you that the dominant eigenvector, there is a local basis where it can be taken to be all of the same sign, but positive or all negative. But the point is that if this is satisfied, that really if you do projective measurements on this basis, then the distribution of this measurement is informationally complete. So there is a one-to-one correspondence between the probability distribution of your measurements and the wave function. So the wave function would be just the square root of p, okay? So if you do generative modeling of this probability distribution, the capital P, and you learn like a parameterized model of it, same as before, then you can just take a square root of this probability distribution and you will get a wave function, like a neural network wave function. Yes? So the positivity the assumption essentially allows us to restrict ourselves to measuring one basis. And just looking at the measurement in one basis is enough to identify uniquely the wave function. And I'm going to talk, hopefully, maybe not, of the case where, this assumption doesn't hold and even mixed state. Of course, it's a bit more complicated, but it's possible. Yeah. Yeah. Well, if you use this, you would not. No. Well, you have to change your basis. And then you have to, well, in that case, you have to, first of all, you have to really build a neural network which capture a mixed state, not a pure state. if you want to learn a mixed state. Yeah. 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 But here, yeah, because here what I'm really here doing is just, learning a probability distribution. There is no quantum in some sense. Yeah. But yeah, it's all classical. Well, I mean, these wave functions are kind of classical at the end. There is no sign structure. But in this case, that's why we use neural network. But then to do just simple unsupervised learning, if you have a mixed state, then you really have to build like a mixed density, like a mixed neural network state, which we did. Yeah, and hopefully I'll show. But anyway, so I'm gonna move on. Once we have the suppose that we did this learning and we have this neural network, then we can do measurements. That's kind of why we want to do this, right? And so we can measure diagonal observables in that basis. That's trivial. It's just like a classical average over this probability distribution. So we use Monte Carlo. We sample this distribution and measure, the magnetization of some spin model in the sigma z basis. That's just a classical average. We can also do off diagonal observable. That's just a simple trick that you reweight your expression, and then you can still compute this average as a classical average of this is called local observable. And sure, you have this exponentially large sum here, but the point is for all local observable of interest, like correlation function, this is really order 1. And I am gonna have an example here. For example, if you look at the magnetization at sigma x, then really this matrix element for like sigma x between two states, it's really one element only, where you flip this spin and you leave the other unchanged. So as a result, we can learn, for example, like a wave function. This is a 12 by 12 IZ model, so 144 spins. That's substantially larger than what you could do like full tomography, of course. And then we can measure observables with the neural network and compare, for example, to quantum Monte Carlo. And here we train in the sigma z basis, where the wave function has all these nice properties. And we measure, for example, sigma z magnetization. But then we can also use this trick and compute sigma x magnetization just by training in one basis. Yes. Yeah. Sorry, this is a number of Monte Carlo steps. Yeah, sorry, I was going a bit too fast here. So, I mean, the fact that so I can actually look here. This is more generic expression of but since this observable is diagonal in this basis, then it just reduces to this average. I can sample this probability distribution using Monte Carlo. And so I can draw this given number of samples from this distribution through standard Monte Carlo, and I can just evaluate this sum using only a polynomial number of samples. Yeah, to generate this sigma. Well, I mean, the error goes down as the square root of the number of samples, just like in standard Monte Carlo. So you're approximating. I mean, this is nothing really quantum going on here. It's the same that you would do in a classical stab mech when you compute the 2D IZ model and you do Monte Carlo on that. Then, of course, there is a ergodicity issue. So I mean, this is all a different. If this, you might need different type of updates actually to get bias distribution. So if you can sample the distribution correctly, I mean the error goes down as 1 square root of n regardless, but you might bias your estimators if you're not sampling the distribution correctly. Which means that we have to take care of the update that we do in the neural network, but it's all very technical. But in general, it can be done. And in fact, I mean, in this case with the error, essentially it doesn't even show. Yeah. Well, I would say that full tomography, really you have to write down the state completely. So if you want to do it for 144 spins, I mean, you can get to 8 spins, 10, but then, yeah. Yeah. Well, full tomography, I mean, yeah, but how do you write the state, right? I mean, what's at the end of the day, what do you get out of the full tomography? When I say full tomography, exactly, that's what I mean. Yeah, and that case is really exponential in the number of spins, and it would not be applicable for like, yeah. All right, so this is kind of all simulated data. This is what we did, a few years ago with data with quantum Monte Carlo. And before I'm going to show you like an application to a real experiment. And so this is a collaboration that between different people, and the experiment we did together with Misha Lukin in his lab. And so let me just tell you briefly what the setup is. So what they have cold neutral atoms. Those are rubidium atoms. They trapped in optical tweezers. Those are like tightly laser beams. They're so tight that at most one atom can be trapped in their focal point. Okay, and so they have a way to create defect-free arrays just by remove entropies, but maybe it's a little bit technical too. What they can do, they can really they can create a defect-free arrays of rubidium atoms at a really low temperature. And of course, at low temperature, everything stays in the ground state. Nothing's really interesting happening, but you can, shine a laser drive resonantly and excite those states. They undergo like Rabi oscillation. And again, nothing interesting, but as you bring this thing close together, those are neutral atoms, but they still have like van der Waals interaction, okay? And the point is that when this excited state that you drive with your laser, it's a very highly excited state. It's like a Rydberg state. Maybe it's like a n equal 100 in shell. Then the interaction between nearby atoms in this state is so strong. It's about 10 to the 14 stronger than interaction between two atoms in the ground state. So effectively, you create this Rydberg blockade that two nearby atoms cannot be simultaneously excited in the excited state. Okay, so you can have patterns like this, but not two atoms in the same Rydberg state nearby. And so, essentially, leveraging this property, they engineer some interesting phases. And the Hamiltonian that they use essentially boils down to this. There is some chemical potential, this is the tuning. This is transverse field with the proportional to the Rabi frequency that drive this Rabi oscillations. And then you have this interaction, which is, as the plus sign, so it's really antiferromagnetic, if you will. It doesn't want nearby atoms to be in the same state. Okay? And the simplest case, you have this nearest neighbor blockade. So this platform, it's really a platform to simulate Ising physics, because this is an Ising Hamiltonian. Okay? Once you write down this in terms of sigma j. And so the phase diagram now, if you look at the small and negative detuning, then this is positive, and all the atoms want to be in the ground state. And when this is large, all the atoms are large and positive, all the atoms want to be in the excited state, but they can't, right? Because there is this blockade. So effectively, depending on what's the radius between the atoms and how many high order term you keep here, you can drive the system into different broken symmetry states. Here, like nearest neighbor blockade, you create this up-down, antiferromagnetic order. If the interaction range is larger, you can start having blockade at 3, distance 3, and distance 4, etc. Okay? And so this transition, that's the one that we looked at, is really like a Ising universality class. It's like a simple transfer field Ising model, if you will. And the interesting property for me, for the one doing the neural network part, is that this Hamiltonian is stochastic indeed. So the wave function ideally is positive in the atomic occupation number basis. So I say ideally because it's a real experiment, right? So of course, when they do this transition, which is just like an adiabatic laser sweep, of course you pick up complex phases, and your state, of course, get mixed. So this is an approximation that we are making, and we did some simulation before and see that the purity wasn't that too bad at the end of this sweep. And so we only use measurements in the occupation number basis, which is also were the only one that they could produce. And the reconstruction, now I don't want to explain this, but the reconstruction goes essentially as same as I said before. We just have some extra layer in the neural network to correct measurement error, which turns out to be helpful. But I mean, if you're interested, I can talk about this offline, but I'm running out of time. And so we did an experiment with the 8 atoms because in this regime we could do ab initio simulation and actually verify the reconstruction. And this is kind of the setup. We do this sweep in the tuning, and at various time state, we halt the experiment and do projective measurement. Just fluorescence imaging atoms, and we get a bit string with 1 if the atom was in an excited state, and 0 if the atom was in a ground state. Okay, and we do this for many, many time steps. From all the atoms in the ground state here, deep into this Z2 order phase. And we know we can essentially derive the structure just by doing perturbation theory. We can look at the structure of the final state. And this is kind of interesting because you can see that there is this domain wall here where you have 2 atoms in the ground state which fluctuates around these 2 bonds. So we expect to find entanglement when we take this bipartition. Here there are strong quantum fluctuations. Of course, they cannot measure entanglement. It's kind of what was one of the motivations. And so when we can train the machine, and then we can compare the experimental value with the neural network, for example, the excitation density profile. This is something that you just look at the B string and you can tell. So they have access to this measurement. So you can see everything is on the ground state, and as we sweep into the Z2 phase, we observe the emergence of this antiferromagnetic order. Okay, and the prediction kind of match nicely the experiment, which is expected because it's just a diagonal. I mean, if it wouldn't, it would be a problem. Okay, but then we can also, this is just the average value, but we can also look at the average transverse field. And so this measurement was not available in the experiment, so they could not measure this transverse field. And so we can compare our prediction with full Lindbladian simulation, which is a 0 parameter simulation. So there is some discrepancies, of course, because we are making the assumption that the state is pure and positive, which is, especially here, at this point of the sweep, read the state as some mixing and it picked up complex phases. Yes. Well, the Hamiltonian is, but the Hamiltonian is exactly stochastic, but then of course in the lab you have dissipation, and the laser sweep is not perfectly adiabatic, and you have like the phasing and spontaneous decay. So it's, I think by the end, you definitely are not in this assumption that your state is pure and positive. Yes. So this is, yes. So I mean, it's a way essentially to gather extra information about your experiment in some way. Yes. Yeah, that's good. That's totally correct. Yeah. Yeah, I mean, for eight atoms, the Hilbert space is so small that you could get away with it. But I can show you what the problem is. Yeah, so sigma x, this would be the expression for sigma x, and here this probability you would use the inverse of the histogram with the frequency, if I understand correctly, right? It's fine. The problem is that when you have a big Hilbert space, when you get one of data point from your histogram, and then you look at the wave function where one of these spin is flipped, and that might be 0 because you didn't get any data for that configuration. And when your Hilbert space is very large, that's most of the cases like this. Most of the cases you won't have data for that point because you're looking only at a very small fraction of the space. Well, yeah, I don't know. Yeah, then it's a bit uncontrolled at that point. It's hard to understand what's going on. Okay, and yeah, so like the last thing is that we can essentially use the learn wave function to calculate entanglement entropy, which is it's kind of the initial motivation, and really, provide a way to certify in some way the entanglement in the hardware. And the entanglement entropy, second Rayleigh entropy, can be computed as like average value of the swap operator, where you make two identical copies of the system and you swap configuration on the subregion that you're looking at. And you can do this in the lab. Rajibul Islam, he was actually here, posted in Chris Monroe group. He did it a few years ago, where they really made two copies of the actual system in the lab, and they did quantum interference to compute this entropy. Beautiful experiment, but it's kind of hard to scale up. And you have to really design the experiment just to do that, right? So the idea is kind of, again, to offload, some very computationally, experimentally costly operation to the neural network. So we learn a neural network and then we swap the two networks instead of the experiment. And so overall we get a nice agreement, and we can also observe quantum fluctuations in the let's say, mutual information, but for pure state is the same, where we expecting them to be. And so a property we know is that the entropy that we get is really a lower bound on the entanglement that the same state with the complex space phases would have. So we are bounding entanglement from below, which is nice, I guess. All right, so I'm actually, that's 45 minutes, right? So I'm actually out of time. There's much more I wanted to say, but I spent a bit too much in the intro. Let me just say that we did the same thing for quantum chemistry ground state. So here you don't have this assumption anymore. You really have like a positive and negative states, and this is a collaboration with IBM. And we're working with experiments now, and even in this case for small molecules, we were able to essentially learn these states from VQ, variational quantum simulation in their hardware. Okay, but I don't have time for this, so I'm just going to conclude. So overall, like the point that hopefully I got across is that this type of algorithms, generative models, they can be repurposed quite easily to capture, to learn states from data. And for the cases that we study, we were able to extracting entanglement entropy from cold item wave function, which is pretty interesting to me. And well, for the quantum chemistry simulation, we essentially proved that we could reduce the overhead in the measurements that you need to get to chemical accuracy by 3 or 4 order of magnitudes compared to the actual run in the hardware. And of course, we can do extensions. So we did extend this framework to like mixed states using 2 different approaches. And I would say that the most interesting question to me is really comparing 2 different ways to learn quantum states. So typically in condensed matter physics, what we do is we start from some microscopic model, some Hamiltonian, and we want to get the ground state, or we want to get the Green's function of it. And here it's really a model driven. So we use MPS, quantum Monte Carlo, and each of these methods come with its own notion of complexity. If you use an MPS, your number of parameters is going to grow exponentially with the entanglement, something like that, more or less. If you do quantum Monte Carlo and you have a sign problem, then you get an exponentially large overhead due to the fact that you're sampling the wrong distribution. And then we have this other approach now that you really build this thing in the lab, and you let the hardware solve your problem, in the sense that in this black box you do have the ground state, you have the solution, and you can query through measurements, and then you're trying essentially to reverse engineer the wave function from data. And so again, we are trying to understand a good measure of complexity for this type of approach. It's not yet completely clear. But kind of the question is really, do these 2 methods belong to the same complexity class? If I could associate an optimization landscape in complexity, would this look like this? Is it easier to retrieve a solution from data? I guess this is really what we are thinking about right now. And the hope is that having the data would be kind of simpler to find the solution with respect to just starting from a model. Yeah. Thanks. Yeah, I know. Yeah. There is okay. There are a few things to be said, I guess. Um, there are some network with a specific structure. Those are called autoregressive, like recurrent neural network or other that they are really, you have a collection of neurons, but it really is only one unit, something like, an IPEPS or like this type of network, and then you unroll it and you get your spin chain. So people have been trying to, try to optimize this thing on small system and then unroll it to infinity and see, and they got like kind of decent results for that. Kind of this framework, which is like more data driven, um, so it's applicable to the NIS, nearer term technology. We know tens of 100 qubits. I don't think they're gonna scale up very well when you go to thousands or more, just from experience. So right now, but these devices are available today. So kind of we're focusing on trying to get the most out of for like today's technology, which is it's gonna span next 5 or 10 years. Then thermodynamic limit is always hard when you try to do this type of scaling with a finite size, especially when when you have data. So, but yeah. And regarding like getting the physics out of the network, like interpretability, that's also a very important question people are looking at. I would say um, usually you don't. Um, just crack the network open and see if you learn something about the physics of the underlying system. Um, some cases they show, but I'm not sure how cherry pick those were, because there are many solutions usually in this landscape that are equivalent.